Okay, so in the following video, we will determine whether the following series converges or diverges. As always, we first look at the problem intuitively. So we have here a really complicated looking sequence that we are then trying to sum the terms of from 1 to infinity. This is a very complicated looking series. But if we look at this intuitively, can we perhaps simplify our intuitive feel for it? Well, again, we have a fraction, so we look at the dominant terms top and bottom. So as n increases to infinity, sure, n squared goes to infinity, root of n goes to infinity, and 2 to the n goes to infinity. But on the numerator, we have two positive powers of n and an exponential function. Even though these two are large, as n tends to infinity, we know from the hierarchy of functions that an exponential function will be infinitely larger than positive powers of n. So the numerator is approximately 2 to the n. Now on the denominator, as n increases to infinity, e to the n goes to infinity, ln of n goes to infinity, but again we know from the hierarchy of functions that exponential functions are infinitely larger than logarithmic functions, and so the dominant term on the denominator is e to the n. So this very simple looking series is approximately the same size intuitively as the original very complex looking series. Now is this a p-series or a geometric series? Well, this is a classic geometric series if we regroup 2 to the n over e to the n as 2 over e all to the n. 2 over e is a constant, and if you remember, e is about 2.71828, so e is larger than 2. Therefore, r, being here 2 over e, is a positive number smaller than 1. So what we have here is a convergent geometric series. So this is a real number. So this converges. If you want by the geometric series test. One of the simplest tests, if r is an absolute value smaller than 1, which is the case here, then the geometric series converges. So we have the intuition. This complex original looking series is roughly the same size as this convergent, therefore finite geometric series. All that remains now is to show that this approximation is good enough, that our intuition is valid. So of course we will employ here the limit comparison test, and all we have to show is that the ratio of the original sequence over the new sequence will approach some positive real number. And of course we will not use the simplified form of the new sequence for Bn, but the original form, the original ratio of the dominant term on top and dominant term on the bottom. And you will see why very quickly. And again, this step of the limit comparison test is the verification, the confirmation that our intuition here is good enough to conclude that because the new series converges, then the original series converges as well. So let's rewrite the original sequence, an. Let me rewrite root of n as n to the 1/2 to clearly see it as a positive power of n. If we divide now by bn, we of course multiply by its reciprocal. So e to the n over 2 to the n. And now again we will pair up dominant terms with one another. So if you notice here, the numerator is divided by 2 to the n. So I will bring this up as a times 1 over 2 to the n. Over, let's rewrite this first. And then if you multiply e to the n on the numerator, if you send this down as its reciprocal, so if you divide twice, you get, of course, the same thing. 1 over e to the n, right? If you divide by 1 over e to the n, same as if you multiplied by the reciprocal, which is e to the n. Now you can see, if we multiply the numerator originally by 1 over 2 to the n, we divide each term by the dominant term from the numerator. And if we multiply this by 1 over e to the n, then we divide each term by the dominant term from the denominator. So on the numerator, we will get n squared over 2 to the n plus n to the 1/2 over 2 to the n plus 1 2 to the n over itself over e to the n over itself, which is 1, plus ln of n over e to the n. And now we can take full advantage of the hierarchy of functions. On the numerator, we have two positive powers of n. Both tend to infinity as n tends to infinity, but they are divided by, in each case, 2 to the n, an exponential function. The exponential function in each case is infinitely larger than the positive power of n, and by the hierarchy of functions, both of these therefore shrink to 0. On the denominator, again we apply the hierarchy of functions. Sure, ln of n tends to infinity as n tends to infinity, but it is divided by an exponential function, which is infinitely larger than the logarithm. And so again, by the hierarchy of functions, this ratio tends to 0. And so in the end, the ratio of an over bn, the original over the new sequence, will be converging to 1 over 1, therefore approaching quite simply 1. So as n tends to infinity, the ratio converges to 1. Therefore, as n becomes larger and larger, the fraction an over bn is approximately 1, getting closer and closer to it. If we multiply by bn, this means that an is approximately the same size as bn. And so if we then sum on both sides, then the original series from 1 to infinity will be approximately the same size as the new and simpler series, again summing from 1 to infinity. So all of this work is simply to confirm that our intuition is correct. So because the new simpler series converges as it is a convergent geometric series, then the initial complex looking series will converge as well by the limit comparison test. So let's write this down as our conclusion. So this implies that the initial series converges by the limit comparison test, which I will write as LCT. And that's it.